Welcome back to Diary of the Cosmos. Tonight we drift toward a possibility so vast that it changes the meaning of every beginning we have ever imagined. There is a quiet assumption hidden inside almost every human thought about the universe. That everything began once. A first light, a first expansion, a first moment. A beginning so absolute that nothing meaningful could exist before it. For generations, this image has lived at the center of our cosmic imagination. A universe born from a brilliant emergence, space unfolding, time awakening, matter learning how to become stars. And somewhere within that story, eventually, galaxies turned, worlds cooled, life opened its eyes. It is a beautiful picture, and in many ways, it is also true. Our best observations still tell us that the observable universe emerged from an early state that was hotter, denser, and far more compressed than anything we can naturally compare to the world around us. The oldest light we can see still carries the memory of that era. The cosmic microwave background. A faint afterglow stretched across the entire sky. A whisper from a younger universe. But there has always been a silence hiding beneath this story. A silence at the edge of the word beginning. Because physics can describe the universe with extraordinary confidence for almost all of cosmic history. And yet as we move closer and closer to the first fractions of the first second, our equations begin to tremble. Density rises, temperature rises, curvature rises. The mathematics pushes inward toward a place where all familiar quantities appear to become infinite. A singularity, a word that often sounds like an answer. But in truth, it is more often a sign that the story has reached the edge of what the model can currently say. Not the end of reality, only the end of clarity. And it is precisely in that darkness that one of the most haunting ideas in modern cosmology begins to form. What if the Big Bang was never the true beginning? What if it was only the inside view of something larger? Something hidden behind a horizon no observer inside our universe could ever fully cross in reverse. A black hole. Not merely one object among the stars, but the larger structure whose interior may already be the universe we call home. The thought arrives slowly. At first it sounds like poetry, the kind of cosmic metaphor we invent because the universe is too large to emotionally hold. But this idea does not survive because it is poetic. It survives because some versions of our physical laws allow space-time to be interpreted in ways far stranger than our intuition was ever built to tolerate. A black hole from the outside is a region of no return, a surface where escape velocity exceeds the speed of light, a horizon beyond which all outward paths bend inward. To an external observer, it appears as an ending. Matter falls, light reddens, time seems to slow. The horizon darkens into permanence. But inside the mathematics of general relativity, horizons are not merely endings. They are boundaries between different causal stories, different ways space and time can be arranged. And under some models, what appears from one side as collapse may appear from the other as emergence. A death outside, a birth inside. This is where the first true crack opens in our intuition. Because we are deeply accustomed to imagining black holes as destinations, final states, cosmic graves. But space-time itself does not care about the emotional language we attach to it. Geometry only asks what paths are allowed. And some paths do not end where they seem to end. Some continue into regions that no outside observer can meaningfully describe. Regions where inward and forward begin to blur, where the structure of time itself may redirect, where what looked like an endpoint may instead widen into a new expanding domain, a new interior universe. The darkness does not arrive all at once. Imagine, for a moment, what the sky would feel like if this were true. Not what it would look like, because it would still look exactly like the sky we know. Galaxies, background radiation, the slow architecture of cosmic filaments, the deep red migration of distant light. Nothing in our night sky would suddenly reveal a visible wall around us. There would be no edge painted in shadow, no circular border, no cosmic shell hanging above the stars. Instead, the horizon would be something deeper than sight, a limit built into causality itself. The reason the universe possesses a beginning-like horizon in time. The reason certain regions remain forever beyond direct observational contact. The reason before may not mean what language wants it to mean. And this is where the idea becomes scientifically interesting, rather than merely atmospherically seductive. Because our current cosmological model already contains a horizon structure. The observable universe is bounded not by a physical wall, but by what light has had time to reach us since the early hot phase. A cosmic horizon, a limit on information. A visible edge created not by matter, but by history. Some physicists have asked whether this resemblance between cosmic horizons and black hole horizons is more than coincidence. Whether the universe's large-scale causal structure could reflect the interior geometry of a much larger, collapsed object in another parent cosmos. In that picture, what we call the Big Bang is not the beginning of all existence. It is the beginning of our accessible interior timeline. The first moment from the perspective of observers inside the expanding region. But not necessarily the first event in the larger chain of reality. This is an active hypothesis. Not established cosmology, not a replacement for the standard model, but a serious enough line of inquiry that it has returned repeatedly across decades of theoretical work. The seed of the idea stretches back to earlier proposals that entire universes might form inside gravitational collapse events. Later, bounce cosmologies gave the concept more physical footing. The singularity, rather than representing a literal infinite point, could instead mark the breakdown of classical gravity. At sufficiently extreme densities, quantum effects, torsion, or limiting curvature mechanisms may prevent true infinities from ever forming. Collapse continues. Compression deepens. But before density becomes mathematically impossible, the geometry resists. Not violently, not explosively, more like a whisper of reversal hidden inside the deepest compression nature allows. A bounce. And from the inside of that bounce, expansion begins. To external observers in the parent universe, a black hole remains a black hole. A horizon seals the collapse. Its mass contributes to the surrounding cosmos. Its exterior obeys familiar relativistic laws. But beyond the horizon, the internal geometry may no longer resemble the simple image of matter falling toward a central point. Instead, it may unfold into a new arrow of time, a new cosmic expansion, a new history, possibly even a new thermodynamic story with its own stars yet to ignite, its own galaxies yet to rotate, its own civilizations yet to wonder where everything began, perhaps even its own black holes. And if so, the structure becomes almost unbearably elegant. Universes giving birth to universes through collapse. Each horizon becoming someone else's dawn. Each singularity replaced by a hidden continuation. Each apparent ending preserving the possibility of interior beginnings. Still, caution matters here. This is not proof. There is no observational result today that forces cosmology to conclude we live inside a black hole. The standard Big Bang framework remains the most successful description of early thermal history, nucleosynthesis, structure formation, and cosmic background observations. This hypothesis survives because it may answer a deeper question left open by the standard picture. What truly happens where classical gravity predicts infinity? The answer may not be nothing. It may be new geometry. The silence between collapse and expansion may not be emptiness. It may be transformation. And this is where the emotional power of the idea begins to merge with its scientific discipline. Because the universe, in this model, is not reduced. It is enlarged. Our beginning is not denied. It is contextualized. The first light still matters. The plasma still cools. Hydrogen still gathers. The first stars still burn into existence. Everything we know about cosmic history after the hot, dense phase can remain intact. The only thing that changes is what the word first means. Not first in all reality, only first in our horizon of memory. A red dwarf, small, quiet, and patient beyond imagination. Even now, somewhere in the distant future, such stars may outlive every brighter sun. And if this universe itself was born from collapse, then perhaps endurance is already written into its deepest architecture, not through permanence, but through continuation. Endings outside, openings within. The darkness between them is where our story may truly begin. And yet, even this is only the threshold of the question. Because if a universe can emerge inside a black hole, then the next mystery is even more profound. What would space-time actually feel like from the inside of such an interior? Would expansion still appear natural? Would horizons still resemble beginnings? Would the geometry itself leave subtle clues in the oldest structures we can still observe? Those questions wait just beyond this first horizon. The story becomes stranger the moment we stop asking when the universe began and start asking what kind of event a beginning really is. For most of modern cosmology, the early universe has been described with extraordinary success through a simple and deeply powerful idea: that if we run the expansion of the universe backward, galaxies move closer. Space contracts. Temperatures rise. Matter becomes radiation. Radiation becomes plasma. And eventually, everything we can currently observe converges toward an early state of astonishing density and heat. This picture is not speculation. It is one of the strongest achievements in science. The expansion discovered through galactic redshift, the cosmic microwave background, the primordial abundances of hydrogen, helium, and lithium, the growth of large-scale structure, all of it points toward a universe that once occupied a far more compressed and energetic phase. In that sense, the Big Bang remains real, not as an explosion in space, but as the rapid expansion of space itself from an early hot, dense condition. That foundation does not disappear in the black hole universe idea. It becomes deeper. Because the real tension in cosmology has never been the hot beginning itself. It is what happens when our equations are pushed too far beyond it. As the scale factor shrinks towards zero, classical general relativity drives density toward infinity. Curvature diverges. Temperature diverges. The mathematics points toward a singularity, a place where our description ceases to be physically interpretable. And this is the crucial distinction. A singularity is not necessarily a physical object. It is often a sign that the theory being used has crossed beyond its domain of reliability. Newtonian gravity fails near light speed scales. Classical thermodynamics fails at quantum scales. And general relativity, beautiful as it is, may fail where quantum geometry becomes unavoidable. So the real scientific question is not whether the early universe was hot and dense. It absolutely was. The deeper question is whether that hot, dense state was the first physically meaningful moment, or merely the earliest moment classical gravity Santa gravity can still describe. The darkness does not arrive all at once. This is where bounce cosmology enters the story. A bounce model keeps everything we know about the early hot universe after a certain threshold. The plasma, the cooling, the nucleosynthesis, the background radiation, the later birth of stars. But it refuses to let density become literally infinite. Instead, as collapse deepens toward an extreme curvature regime, a new layer of physics pushes back. In some approaches, this resistance comes from quantum gravity. In others, from Einstein-Cartan theory, where spin and torsion modify the geometry of space-time at enormous densities. And in newer black hole universe models, this pushback can be interpreted as the interior continuation of a gravitational collapse in a larger parent cosmos. So the Big Bang survives. But it changes character. No longer an absolute origin, now a turning point. A rebound, a hidden reversal inside a horizon. To feel how profound this is, imagine following matter in a parent universe as it collapses under its own gravity. A giant star, perhaps far beyond the mass scales we normally discuss. Or a larger cosmological collapse event. Gravity gathers everything inward. The curvature strengthens. Time and radial structure begin to distort. To outside observers, the process stabilizes into something familiar. A black hole forms. An event horizon seals it from the rest of the surrounding universe. Its mass remains measurable. Its exterior space-time behaves as expected. But beyond that horizon, the classical picture of falling forever inward may be too simple. As densities approach the regime where quantum corrections matter, the collapse may never truly reach a literal zero-volume point. Instead, geometry itself may resist perfect compression, like a spring that cannot be seen until it is already fully compressed. Not a mechanical spring, of course, a geometric one, a hidden stiffness built into reality. The collapse slows. The inward paths converge. Curvature reaches its maximum physically allowed form. And then, instead of ending, the metric transitions. What had been contraction becomes expansion, not backward in the emotional sense, forward in a new internal arrow of time. This is the bounce. For observers living inside that new expanding region, it would not feel like a rebound from a prior universe. It would feel like the beginning of everything. Space would appear to expand in every direction. The earliest visible epoch would still resemble the fire of the early universe. Matter would still thermalize. Radiation would still dominate. The first atoms would still emerge after cooling. Nothing about the lived physics of early cosmology would feel artificial. The observable evidence we possess today would still remain consistent. This is why the hypothesis is scientifically elegant. It preserves almost all successful predictions of standard cosmology after the bounce threshold. It simply replaces the singularity with a physical mechanism, a continuation, a bridge, a softer answer where the old mathematics used to become infinite, a quiet reversal hidden inside impossible density. And once that idea settles in, another realization follows. The Big Bang may not have been a bang at all. The phrase itself has always been slightly misleading. It suggests violence, a blast, a point source detonation and into surrounding emptiness. But the universe did not expand into anything we can meaningfully describe. Space itself expanded. Distances emerged. Causal separation developed. The bounce interpretation preserves this beautifully. Because what expands after the turning point is not debris from an explosion. It is geometry, the shape of accessible space-time itself. A red dwarf, small, patient, almost eternal. In the far future, such stars may survive when every brighter star has already faded. And strangely, bounce cosmology shares that same emotional architecture. It replaces abrupt endings with prolonged continuity. A collapse that seems terminal, a density that appears final. And then, hidden within the most compressed state, the story opens again. Not louder, quieter, more deeply. Still, scientific honesty matters. A bounce is not yet proven. There is no direct observation that uniquely selects one bounce mechanism over all alternatives. Inflationary cosmology remains extraordinarily successful in explaining flatness, horizon structure, and primordial perturbation seeds. Any bounce model must recover these same successes. Some do so elegantly, others remain incomplete. The black hole interior version is compelling precisely because it connects two singularity problems at once. The singularity of the Big Bang and the singularity predicted at black hole cores. Instead of treating these as separate failures of classical gravity, the model suggests they may be the same failure viewed from opposite sides of a horizon. A collapse in one frame, a beginning in another. This symmetry is what gives the idea its haunting power. Because it suggests that our earliest moment may not be isolated from the rest of reality. It may be causally descended from something older. A structure beyond our observational reach, yet not beyond physical possibility. And this naturally changes how we interpret the word before. In standard public language, asking what happened before the Big Bang often sounds meaningless, because time itself is said to begin there. But bounce models soften that absolute claim. Time, as we measure it inside our expanding universe, may begin at the bounce. Yet the larger physical chain of causation may continue through a parent collapse phase, not necessarily before in the naive clock sense. More like an earlier branch in a wider geometric process, a deeper lineage of space-time. This distinction is subtle, and it is exactly the kind of subtlety DOTC thrives in, because the emotional consequence is enormous. The first light of our universe may still be sacred, still real, still the dawn of everything we can ever observe. But it may no longer be the dawn of all existence, only the first light that belongs to our horizon of inheritance. Every galaxy we have ever mapped, every atom in every ocean, every memory carried by starlight, all of it may descend not from absolute nothingness, but from a hidden gravitational turning point. A moment where collapse became interior expansion, where death in one cosmic frame translated into birth in another. The silence between those states is where this entire theory breathes. And it also raises a difficult challenge. If the Big Bang was a bounce, what traces could survive the transition? Would anything from the parent collapse remain encoded in our universe? A preferred direction? A subtle spin bias? A strange asymmetry in the oldest galaxies? A large-scale memory written into primordial geometry itself? These are not merely poetic questions. They are the bridge between elegant theory and possible evidence. Because a good cosmological model cannot survive forever as atmosphere. Eventually, it must risk contact with observation. That is where the black hole universe hypothesis becomes even more fascinating. Some modern discussions suggest that if the parent black hole possessed angular momentum, traces of that rotational inheritance might remain visible in the statistical orientation of very early galactic structures. Nothing conclusive, nothing remotely final, but enough to transform this from pure metaphysics into a testable scientific direction. The darkness does not arrive all at once. It deepens through structure, through clues, through tiny imbalances in the oldest visible light. And that is where our next horizon waits. Because if the beginning was truly a bounce inside a black hole, then the most profound question is no longer philosophical. It becomes geometric. What would the inside of such a space-time actually look like to those living within it? Would it resemble ordinary cosmology? Would expansion itself be the natural signature of interior curvature? Would the horizon that created us still echo in the shape of the universe we can now observe? Those answers live deeper inside the geometry. By now, the idea no longer feels like metaphor. The early universe can remain real. The hot, dense phase still stands. The bounce offers a physical alternative to the singularity. But a deeper question now begins to pull at the edges of the mind. If our universe truly emerged from the interior continuation of a black hole, then what would space-time actually feel like from the inside? Not emotionally, geometrically. This is where intuition begins to fail in the most beautiful way. Because almost every mental image we inherit about black holes is shaped by the outside view. A dark sphere suspended in space, a glowing accretion disk, light bending around a shadow, matter spiraling inward toward disappearance. All of that is true, from the outside. But the outside perspective is not the one we are testing anymore. We are asking what the interior observer would measure, what clocks would say, what distances would do, what the sky would become if all of cosmic history itself unfolded beyond an event horizon. And the answer begins with one of the most important corrections in all of relativistic thinking. Inside a black hole, the meaning of inward is not what human intuition wants it to be. Outside the event horizon, radial distance behaves in the familiar way. You can move closer to the center. You can move farther away. The direction is spatial. But once the horizon is crossed, certain coordinate descriptions reveal something astonishing. The radial path toward what classical relativity labels the singularity behaves less like a place in space and more like an unavoidable direction in time. Not a destination you may choose to avoid, a future you are carried toward. This is the first reason the black hole universe idea becomes scientifically interesting. Because if classical gravity fails before that future reaches infinite curvature, then the inward future may not terminate. It may transform. And if it transforms through a bounce, then what follows is not more collapse. It is an expanding internal timeline. To any observer born after that transition, the geometry would not feel like life inside a tunnel or chamber. It would simply feel like a universe, expanding space, a cosmic horizon, distances between large-scale structures increasing, the ordinary logic of cosmology. This is why the phrase, "inside a black hole," can be misleading. It suggests enclosure, walls, a cavity inside a larger object. But general relativity does not describe the interior that way. It describes a causal structure, a rearrangement of what directions in space-time are possible. The event horizon is not a shell you could touch. It is a boundary in the geometry of paths, a one-way informational threshold. From outside, nothing meaningful escapes. From inside, history unfolds forward. The darkness does not arrive all at once. Imagine the first moments after the bounce in such an interior. Not a spark in emptiness. Not debris expanding into pre-existing space. Instead, the metric itself begins to open. Scale factors increase. Causal regions separate. Thermal density fills the earliest visible universe. Radiation dominates. Exactly the kind of physics our observations already demand. This is why the model can remain compatible with established cosmology after the first tiny fractions of time. The universe would still cool. Baryons would still stabilize. Hydrogen and helium would still emerge. The cosmic microwave background would still later preserve the memory of recombination. Galaxies would still grow from density fluctuations. Nothing in the ordinary lived experience of cosmology would need to announce, "You are inside a black hole." The clue would live not in appearance, but in the deeper structure of initial conditions, in the shape of the earliest geometry itself. And this leads to the most elegant part of the idea. The observable expansion of our universe may not be a separate phenomenon from the black hole's interior causal evolution. They may be the same thing. What outside observers describe as the inaccessible future of collapse, inside observers experience as the forward flow of cosmic time. A collapse there, a beginning here, the same geometry, different causal stories. This duality gives the hypothesis its extraordinary philosophical weight, but it also introduces a scientific challenge. Wouldn't we notice some preferred center, some direction pointing back toward the parent collapse? At first glance, it seems obvious that we should. Human intuition desperately wants interiors to have centers. Rooms do, planets do, stars do. But the relativistic interior continuation is not a room. After the bounce, the geometry can evolve into something mathematically similar to the large-scale homogeneous expansion already used in cosmology. No meaningful center need remain accessible to internal observers. The expansion can appear isotropic, uniform in all directions, exactly the way our current observations describe the large-scale universe. So the model survives the first intuitive objection. No, we would not necessarily feel ourselves falling towards some hidden middle point. From the inside, there may simply be no such physically meaningful direction left to access. A red dwarf, quiet, steady, its light barely changing across unimaginable spans of time. There is something emotionally similar in the way this geometry behaves. What once seemed like terminal collapse softens into continuity. The universe inherits not the violence of an ending, but the patience of transformed curvature. The event horizon becomes less like a prison and more like a translation, one causal language rewritten into another. Still, geometry alone is not enough. The real scientific value lies in whether such an interior would leave subtle fingerprints. And this is where modern discussions have become especially fascinating. If the parent black hole carried angular momentum, then the interior continuation may not be perfectly symmetric. Rotation in the parent geometry could influence the initial conditions of the expanding internal universe. Not dramatically, not as a visible cosmic spin axis carved across the sky, but statistically, softly, as tiny asymmetries in how the oldest large-scale structures orient themselves. This is one reason some researchers have paid close attention to the rotational distribution of very early galaxies. If ancient structures show an unexpected preference in spin direction, one possible, though far from proven, interpretation is inherited angular momentum from apparent collapse. This remains an active hypothesis, not evidence, not consensus. But it is one of the first places where interior geometry risks contact with observation. And that risk is what transforms a haunting idea into legitimate cosmological inquiry. Because science becomes most beautiful when its most poetic possibilities still kneel before data. The darkness does not arrive all at once. It bends, quietly, like light around a horizon. There is another subtle consequence of living inside such an interior geometry. The meaning of outside may no longer be operationally useful. We can say the parent universe exists. We can describe a larger collapse event. We can imagine an external frame in which the black hole formed. But none of that lies inside our causal reach. No signal can cross the horizon backward into our accessible history. No observation from within our universe can simply look outside to confirm the parent cosmos. This is why the hypothesis remains difficult. Its explanatory beauty is immense. Its observational accessibility is limited. Yet this limitation is not unique to this model. Cosmology already lives with horizons. Even in standard models, there are regions forever outside what light has had time to show us. The black hole interpretation does not invent hiddenness, it deepens it. It suggests that the reason our cosmic horizon behaves the way it does may be rooted in the inherited causal architecture of a much larger gravitational event. And perhaps the most haunting implication of all is this. From the inside, the event horizon would not feel like crossing into darkness. It would feel like being born too late to ever witness the collapse that made you possible. All of cosmic history would unfold after the decisive transition. Our oldest light would still only show the cooling aftermath. Our equations would still trace backward toward extraordinary density. And yet the true origin would remain just beyond the last mathematically visible surface. Not absent, only hidden behind transformed geometry. This is the scientific summit of the black hole universe idea. That a black hole is not merely an object in the universe. Under certain models, it may be a mechanism through which universes inherit time. Collapse translated into expansion. Exterior death translated into interior history. A horizon becoming the first page of an entirely new chronology. And yet, once geometry suggests this possibility, a sharper question naturally follows. If such an origin leaves no obvious center and no visible wall, then what remains for us to test? What fragile traces of inherited rotation, asymmetry, or primordial bias might still linger in the oldest galaxies ever formed? That is where theory must finally step into the light of observation. There comes a moment in every cosmological idea when elegance is no longer enough. A theory can be mathematically graceful. It can be philosophically irresistible. It can even solve multiple deep problems at once. But sooner or later, it must risk the one thing that makes science real: observation. This is where the black hole universe idea steps out of pure geometry and enters the oldest visible structures in the sky. The first galaxies, the earliest spirals, the ancient systems whose light has traveled for more than 13 billion years just to reach our instruments. Because if our universe truly inherited its interior geometry from a parent black hole, then some tiny memory of that parent collapse may still survive. Not as a visible wall, not as a hidden center, but as bias, a preference, a statistical whisper in the oldest structures ever formed. And among the most intriguing modern discussions surrounding this possibility is a simple question. Do very early galaxies rotate randomly, or do they seem to prefer one direction? At first, the expectation appears obvious. On sufficiently large scales, the universe should not favor clockwise over counterclockwise spin. Any large sample of distant spiral galaxies should, statistically, distribute close to 50-50. No preferred cosmic handedness, no inherited universal twist. That expectation is deeply aligned with the cosmological principle itself. Large-scale isotropy, no privileged orientation, no special direction. And yet, in several analyses of deep field data, including JWST fields, some researchers have reported an unexpected asymmetry. A larger fraction of early spiral galaxies appear to rotate one way rather than the other. This does not mean the universe has been proven to rotate. It does not mean the black hole universe model is confirmed. But it does create one of the first genuinely atmospheric bridges between elegant theory and possible evidence. The darkness does not arrive all at once. It arrives as imbalance, a tiny statistical lean in the oldest visible wheels of starlight. Imagine looking into the earliest deep fields ever captured. Galaxies so young that their light began traveling toward us when the universe itself was still in its earliest structural adolescence. Small spirals, faint asymmetries, barely enough visible arm structure to infer rotation. And across that ancient sample, the numbers begin to tilt. Not dramatically enough to close the case, but enough to provoke, enough to make cosmologists ask whether this is selection bias, processing bias, local observational effects, or something much older, something inherited. In some published analyses, the ratio has approached roughly 2/3 versus 1/3 in certain deep fields, rather than the expected near symmetry. Again, caution is everything. This remains controversial. Sample sizes are limited. Image classification methods matter enormously. Projection effects remain difficult. Different surveys do not always reproduce the same significance. This is exactly why this section must remain in detective mode rather than revelation mode. Because the most dangerous thing in cosmology is to confuse an anomaly with a conclusion. Still, the possibility is haunting. If the parent black hole that gave rise to our interior universe possessed angular momentum, as all realistic astrophysical black holes do, then some trace of that rotational inheritance may survive the bounce. Not as a dramatic cosmic vortex, not as galaxies literally orbiting some invisible center, but as an infinitesimal handedness bias seeded into primordial geometry, a soft preference in the earliest density perturbations, a tiny asymmetry in the way angular momentum statistically cascades into first-generation galactic disks. This is where the black hole universe hypothesis becomes observationally seductive, because it offers a physical story for why such a bias might exist. The parent collapse rotates. The event horizon forms around a Kerr-like geometry. The bounce transfers not only mass-energy continuity, but a subtle directional inheritance. The interior expanding universe begins with a faint spin memory. Billions of years later, the oldest galaxies still carry that whisper. Not loudly, just enough to notice. A red dwarf, steady, almost motionless in the imagination. Yet even its quiet light contains the memory of angular momentum from the cloud that formed it. The same emotional architecture lives here. Small present asymmetries may descend from ancient initial conditions too distant to ever directly observe. The oldest galaxies may not merely show us what the early universe looked like. They may show us what it remembered. But there is another layer of discipline required. Alternative explanations exist, and they must be treated with equal seriousness. The asymmetry may emerge from survey field orientation, telescope bias, galaxy classification noise, foreground motion effects, large-scale structure anisotropy, unrelated to black hole cosmology. Simple statistical fluctuation. Several authors have explicitly noted that the explanation may lie in ordinary structure effects or observational bias rather than exotic cosmology. This matters deeply for DOTC's truth filter, because the beauty of the black hole universe model is not that it explains every anomaly. It is that it provides one physically coherent route by which certain anomalies could become meaningful. A possibility, not a verdict. And yet, even as we protect that uncertainty, the visual power of this section becomes extraordinary. The James Webb Space Telescope peers into the first billion years. Galaxies emerge not as abstract equations, but as delicate rotating fossils. Each spiral arm a memory of angular momentum. Each preferred twist a possible inheritance from a parent horizon older than our own cosmic time. The darkness does not arrive all at once. It rotates, softly, like a question. This is also where the psychological scale of the hypothesis changes. Until now, everything has been hidden in geometry and horizons. Invisible structures, causal boundaries, mathematical continuation. But here, for the first time, the sky itself seems capable of participating, not proving, not revealing, only hinting. The oldest galaxies become witnesses, not to the parent universe directly, but to the initial conditions that may have shaped their birth. And that changes the emotional gravity of the theory. Because the cosmos is no longer merely something we model backward. It begins to feel like something that still carries scars. Not violent scars, more like fingerprints. A slight asymmetry in the oldest turning wheels of light. A preference too ancient to explain casually. A preference still waiting to be understood. There is a danger here, of course. Human pattern hunger. We are built to see intention in weak signals, meaning in imbalance, stories in partial data. This is why responsible cosmology must resist the urge to romanticize every anomaly. Some anomalies disappear, some become calibration issues, some dissolve when larger surveys arrive, and some become revolutions. The black hole universe hypothesis remains alive because it can, in principle, stand in either future. If the asymmetry vanishes, the theory still survives as a geometric cosmological model. If the asymmetry strengthens across future JWST, Euclid, Roman, and deeper surveys, then the parent spin interpretation becomes far more interesting. This is why Section 4 is not about answers. It is about scientific tension. A theory finally brushing against the oldest measurable structures in existence. A hidden horizon risking exposure through statistical archaeology. And perhaps the most DOTC-like consequence of all is this. The universe may be too young in memory to witness its own true origin, but it may still be old enough to preserve a rotational accent from the collapse that made it possible. A faint accent, a handedness, a preferred whisper in the oldest galaxies. Not enough to convict reality, enough to keep listening. Because once the possibility of inherited spin enters the story, the final question becomes less observational and more existential. If our universe really carries memory from apparent collapse, then what does the word outside even mean anymore? Does outside describe a place, a prior frame, a lost causal ancestry? Or is it simply a word our inside-born minds invented? Because horizons always make us imagine something beyond them? That is where the final section must go. Beyond evidence, beyond geometry, toward the meaning of a universe whose beginning may have been someone else's event horizon. By the time we arrive here, the universe has already changed shape in the mind. What began as a question about black holes and beginnings has quietly become something deeper, a question about language itself. Because if our universe truly emerged from the interior continuation of a black hole, then the final mystery is no longer merely how it began. It is whether the words we use for origin were ever capable of describing it at all. Before, outside, beyond. These words feel natural to us because human thought was built inside rooms, landscapes, skies, and horizons that can be crossed. Every wall implies another side. Every edge implies extension. Every darkness implies another space waiting past it. But cosmology has always warned us that intuition is provincial. The mind evolved for valleys and weather, not for event horizons, not for causal geometry, not for universes that inherit time through collapse. So when we ask what exists outside our universe, we may already be asking the wrong kind of question. Not because there is nothing beyond, but because outside may be a spatial word forced onto something that is fundamentally causal. A black hole's event horizon is not a wall. It is not a shell suspended in higher dimensional emptiness that some spacecraft might one day fly through. It is a boundary in the allowed structure of information, a limit on what causal chains can communicate, a one-way translation in the geometry of time. If our universe is the interior continuation of such a horizon, then the parent cosmos may indeed exist in a perfectly meaningful physical sense. A larger frame, an older collapse, a history in which the black hole that became our accessible universe once formed. But from inside our own causal story, that parent frame is not outside in the ordinary sense. It is inaccessible ancestry, a prior geometric lineage, a history that made us possible without ever becoming observable to us. The darkness does not arrive all at once. It arrives as humility, because this is where the black hole universe hypothesis becomes less about structure and more about epistemology. The universe may not hide its origin maliciously. It may simply encode it beyond the kinds of questions internal observers are capable of operationally verifying. Our oldest light still only reaches back to recombination. Our equations still only penetrate reliably toward the earliest hot, dense epochs. The bounce, if real, sits deeper than direct observational memory, and the parent collapse lies deeper still. The result is almost unbearably elegant. A universe born from an event it can never directly witness. A civilization asking about a collapse whose horizon erased every route of direct return. A cosmos whose true ancestry may only survive as inherited asymmetry, thermodynamic direction, or primordial geometric bias, not as sight, only as consequence. This is why the idea of universes giving birth to universes has such unusual emotional gravity. Under some speculative extensions of black hole cosmology, every black hole may seed a new expanding interior domain. Not proven, not established, but physically imaginable within several broader baby universe and bounce frameworks. A star collapses, a horizon forms. External observers see a black hole. Inside, a new thermodynamic arrow opens. Space expands. A new sky begins. Its inhabitants call that moment the beginning of time. And somewhere, billions of years later, they wonder whether they too are inside a black hole. The structure becomes almost recursive in its beauty. A cosmic genealogy. Horizons as birth channels. Collapse as inheritance. Each universe inheriting laws, asymmetries, and initial conditions from the geometry that produced it. A family tree written not in biology, but in curvature. A red dwarf, dim patient, still burning long after brighter stars are gone. There is something deeply similar in the emotional architecture of this final possibility. Reality may preserve itself not through permanence, but through generational continuity, not eternal objects, eternal transitions. Each ending outside becomes the first light of another interior history. Still, discipline remains sacred. This section lives closest to speculation, and speculation must remain clearly marked. We do not know that every black hole creates a universe. We do not know that our own black holes are cosmic wombs for future realities. We do not know whether physical constants would survive such inheritance. These are ideas that extend beyond current evidence. They are useful because they illuminate what the geometry permits, not because data has yet confirmed the chain. That distinction is the final truth filter. And once we preserve it, the existential consequence becomes even more haunting. The universe may not be an isolated object. It may be a descendant, not disconnected from reality, but deeply embedded in a lineage of transformed horizons. The first stars in our sky may descend from the last moments of another cosmic frame. The hydrogen in ancient nebulae may carry the thermodynamic inheritance of a collapse that no signal can ever show us. Even entropy itself begins to feel different, not merely the drift toward disorder within one universe, but perhaps a larger inheritance law across generations of space-time. The darkness does not arrive all at once. It is handed down, quietly, through horizons. And perhaps the most profound shift of all is what happens to the meaning of origin. For centuries, beginnings have implied singularity, an absolute first page, a point before which there was simply nothing to discuss. But the black hole universe idea replaces the romance of absolute beginnings with something more mature: continuity. Our first page may still be real, still sacred, still the earliest readable line in our cosmic book. But the book itself may belong to a library far older than our own chapter. A chapter we can never leave, a library we can never directly enter, yet one whose architecture may still be faintly visible in the way our oldest galaxies turn, in the way horizons shape what can be known, in the way the universe expands from a beginning-like boundary that behaves more like transformed ancestry than absolute origin. This is why the word outside may never have been meaningful in the way we first imagined. Not because there is no parent reality, but because our geometry transforms the question before language can finish asking it. There may be no outside in the spatial sense, only prior causality. No beyond as a place, only a deeper branch in the lineage of collapse and expansion, a translation between histories. And in that realization, the fear leaves the idea. What remains is not claustrophobia, not the image of being trapped inside some cosmic chamber. What remains is wonder. The possibility that our universe is not smaller than we believed, but older in ancestry. Not bounded, but descended. Not isolated, but inherited. Every galaxy cluster, every fading quasar, every cold future red dwarf still burning in the trillionth year. All of it may belong to a history that did not begin with nothing, only with a horizon that, from another frame, once looked like darkness. From ours, it became time. And perhaps that is the most beautiful scientific possibility hidden in this entire journey. That black holes are not merely where information disappears from sight. Under the right conditions, they may be where history changes language. A collapse in one universe, a beginning in another. A boundary translated into chronology, The oldest galaxies still turning above us may be carrying the final whisper of that translation. A rotational accent from apparent collapse. A memory too old to call memory. A trace too subtle to call proof. But enough to let wonder remain disciplined. Enough to let science and awe breathe in the same darkness. This has been another entry in Diary of the Cosmos. Until our next journey, remain with the stars.